All right, so we're continuing our discussion on probability and counting. And this video, it's actually the middle video. We're going to have a total of 5. This is video number 3, so we're smack dab in the middle. This isn't really so much a new counting method, but it's a new form of arithmetic that we're going to use with the last counting method. So in the last video that we watched or that we made, you watched a video about the fundamental counting principle. And what we're going to be using in this video goes hand in hand with fundamental counting principles. So it's not a new technique, but it's a new process to help us do the arithmetic a little bit more efficiently. Basically what it is a new operator. Okay, now operator is not a word that we use a lot in math class. An operator is just one of the forms of arithmetic. So like, for example, a plus, addition, that's an operator. Multiplication, that's an operator. Squaring, that's an operator. Okay, so we're going to learn an operator that's like that, a way to do arithmetic. And this is going to make certain problems with the fundamental theorem of calculus move a little bit faster, be a little bit easier. So with that said, let's get started talking about the factorial operator. So here is our learning objectives: be able to calculate a factorial and then use a factorial to find the number of outcomes. We will be doing this in conjunction with the fundamental theorem of or the fundamental counting principle. There we go. Had to remember the right theorem there. Fundamental counting principle. Okay, so we're not really learning a new technique, but we are learning a process that will help us save a little bit of time when it comes to arithmetic. All right, so with that said, let's start with what is a factorial. Factorial. What is a factorial? Okay, so it is an arithmetic operator . Okay, an arithmetic operation. So just like addition or multiplication or squaring or square rooting, this is an arithmetic operation. So that means we need to know a couple things about it. One thing we'll need to know is its symbol. Symbol. There we go. Okay. Now, all of the different arithmetic operators, they have some sort of symbol. So we know that when we see a little tiny plus sign, a little tiny t, that means addition, right? A plus, right? If we see a little x, that means multiplication. So what is the symbol that means factorial? Well, it's the exclamation point. The exclamation point. That's the symbol for factorial. So the way this will look in a problem is you'll have a number with factorial after it. Okay, so factorials only work on one number at a time. So it's different than like addition, right? With addition, you need two numbers, 2 plus 5, right? It's different than multiplication, where you need two numbers, 3 times 12, okay? Factorial is more like a square or a square root, where it just works with one number at a time, right? The square root of 25. There's only one number there. It's the 25. I'm taking the square root of 25, okay? Factorial is more like that. I'm only taking the factorial of one number. So that's what it looks like when you'll see it in a problem. Now, what it does, how it works, okay? Every different type of arithmetic means something in the physical world, right? Addition means I've got a group of things here, I've got a group of things here. I'm putting those two groups together to get a new total of stuff. Multiplication means I'm counting groups. So I've got a group here, I've got the same size group here, I've got the same size group here. If I want to figure out the total number of things, then I can say, well, there's 3 groups that are the same size, so that number times 3. So it has a physical meaning, right? So the way factorial works, its physical meaning, what it does is it takes the numbers that you're given, whatever number that's next to the exclamation point, okay, and we multiply that number. We multiply the number by every counting number that comes before it. Before is usually one word. I'm not sure. Let's just make that a really big E. Before it, okay? Makes it multiply the number by every counting number that comes before it, okay? So in this particular case, 3 factorial, what that means is I'm going to start with a 3, and I'm going to multiply it by every counting number that comes before it. So again, remember the counting numbers, there's no decimals, there's no negatives, I'm not using 0, just the normal numbers like you learned them in preschool, 1, 2, 3, 4, 5, 6. So I start with 3, the counting number that comes before 3 is 2, the counting number that comes before 2 is 1, and 1 is the smallest counting number. So on all of these problems, you're going to be done when you get to 1. So I've got 3 times 2, which is 6. 6 times 1 is equal to 6. So 3 factorial is equal to 6. Okay, so this is the basic idea of the factorial. I start with the number that I'm given, and then I multiply that number by every counting number that comes before it. Okay? Now, the definition works a little bit funny with certain numbers, with actually 2 numbers in particular. For example, the number 1. There are no counting numbers that come before it. So I start with 1, and I don't multiply it by anything, so I just get 1. So 1 factorial just equals 1, because there's no counting numbers that come before it. Okay. Now, it is possible to do a 0 factorial, which really doesn't even make sense, because there 0, not only are there no counting numbers that come before 0, 0 is not even a counting number. So there's a real sense in which mathematically, by this definition, this doesn't even mean anything. This doesn't even make sense. But it turns out that in places where we use factorials, 0 factorial crops up relatively often. And so mathematicians extended the definition. In addition to doing this, they added a second piece to the definition that says 0 factorial is just always going to be equal to the number 1. Okay, so that's a little bit weird. That's a little bit strange. It's sometimes hard for students to understand why that works, or how it works, or just to remember the fact that 0 factorial equals 1. We're not going to get into any more of the why it works, other than to just say that it was convenient for mathematicians to define it that way. So 0 factorial equals 1. Now, the good news is you don't necessarily have to remember all of these little details. This one is pretty easy to remember. Most people are fine with that. This one, it's a little bit weird. There's only a 1 there, so most people are kind of like, This one, though, is just odd. Okay, so a lot of people don't like that one. So the nice thing is there is a factorial feature on your calculator. So you don't necessarily have to remember all of those rules. You can just use your calculator. And if you're using one of these newer forms of the Texas Instrument calculator, the factorial is in the same menu where we found logarithms and things like that, in the alpha window menu. So if I wanted to do 3 factorial, I would type in the number 3, and then I would go alpha window, and you can see factorial is option number 9, way down here at the bottom. Option number 9 is factorial. So I do 3, alpha window, choose option number 9. That gives me my exclamation point. I push enter. There's the exact same answer that we got just a second ago. We can verify that if I do 1 factorial, I do get 1. If I do 0 factorial, I do get 1 for that also. But there's other numbers that if I do factorial, now it's going to say, you can't do that. Okay, so 0 is as small as we can go. We can't do negative numbers or anything like that. All right. You can, of course, go bigger, right? So if we did, I don't know, 10 factorial, okay, we notice we start getting very big numbers very fast, right? So 3 factorial is 6. If I only go up to 10, that's not very big. Already I've got something that's 3,628,800, right? So 10 factorial is already 3 million. These get very large very fast. If I go up to 20 factorial, now I have to recognize I'm using scientific notation, right? When I get that E, that's scientific notation. So this isn't 2.4. This is 24329, blah, 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 where I move the decimal point 18 spots. Okay, so this is a ginormous number, right? Ginormous number. 2 with 18 numbers after it is a ginormous number. Okay, so we're going to deal with really big numbers when we deal with factorials. So just be prepared for that. So that is the first part of our video, just simply to be able to calculate factorials. In other words, understand the arithmetic that's associated with factorials. Now, how does this come up? As I said at the beginning of the video, we're going to use this in conjunction with the fundamental counting principle. Okay, so before I give you an example on the paper here, let me show you a little something that I did on my calculator. And it's completely contrived just for the purpose of this video. It's not like anybody would ever do this in real life. But what I've done is I've set up my calculator to take a list of numbers, the list 1, 2, 3, 4, 5. There's a list of numbers. And what my calculator is going to do is it's going to take this list of numbers and it's going to shuffle it. So if I run this little program, there's my list of numbers. And when I shuffle it, it becomes this. So now it's not 1, 2, 3, 4, 5. No, it's 4, 1, 2, 3, 5. Okay. And if I run it again, wait for a second, let it do its deal. Now this time I get 5, 3, 4, 2, 1. Okay, almost backwards, not quite, but almost backwards. So what I've got is I've got these 5 numbers and I'm shuffling them. If I run it again, this time I get 5, 3, 2, 4, 1. So very similar, 5, 3, those were the same, only those two switch, okay? And I can do this, really all day long. Wow, I keep getting 5, 3. That seems to be very popular with my calculator right now. Let me do it at least one more time. I want to get something besides 5, 3. There, 5, 2. Well, all right, thank you, calculator. All right, so bottom line, what I'm doing is I'm getting all these numbers and I'm rearranging it. So I'm curious, how many different rearrangements are there? If I'm going to take these 5 numbers and shuffle them to put them into any order, well, here I've got 1, 2, 3, 4. I've got 5 arrangements there. I guess technically this is an arrangement, 6, right? They could end up in the exact order they started in. That could happen. I mean, it seems weird, but it could happen. So I've got at least 6 different arrangements here. I wonder how many arrangements there are altogether. All right, so to answer this question, we're going to consider this as a fundamental counting principle problem. So first of all, let's think about how I would word the problem that we're dealing with, okay? So we have 5 numbers, the numbers 1 through 5, the numbers 1 through 5, okay? So I've got those, the numbers 1 through 5 are in a list. There they are, boom, okay? The numbers 1 through 5, they're in a list, okay? My calculator, I'm going to choose one of them at random. Okay? I'm going to choose one of them at random. So that becomes the first number here. Then I'm going to choose a second one at random. So that becomes the second number in my list. Okay? And so on until I've picked all 5 in a random order. Okay? So that's basically what my calculator is doing. In fact, if I were to show you the little program that I wrote for my calculator in order to achieve this, that's exactly what the program that I wrote does. Is it takes the numbers 1 through 5, it picks one number at random, and then it picks another number at random from what's left, and then it picks another number at random from what's left, and eventually I end up with these numbers in a random order. Okay, so the numbers 1 through 5 are in a list. We're going to choose one number at random, then choose a second number at random, and so on until we've picked all 5 in a random order. So our question is, how many such orderings are possible? Okay, so if I'm going to create an order in such a way as this, how many orderings are possible? That's my question. Okay, so this, I say, is a fundamental counting principle question. So think about when we did fundamental counting principle in the last video, think about the way we approach these problems, what we did. Maybe pause the video real quick and give this a try and see what you come up with. All right, so if we know it's well, let's first talk about how do I know it's fundamental counting principle. Notice I'm choosing one number at a time until I get 5 numbers. So when I read that, that says to me, I have 5 events. Every time I choose a number, that's an event. And I'm going to do this until I've chosen all 5. There's no option for me to choose anything other than 5. So I'm going to have 5 events, and I know all 5 events are going to happen. So that's the conditions that we needed for fundamental counting principle. So as soon as I know I have 5 events, and they're all going to happen, I write down my 5 blanks, and I'm preparing to multiply these events by each other. Now let's think about how many options we have. The first time I've got 5 numbers, 1 through 5. I'm going to pick one of them. In this particular list, we picked the number 4 first. Okay, so I chose one number. There were 5 numbers total that I could have chosen from, but 4 was the one that I happened to choose. So I had 5 numbers. I could have chosen 1. I could have chosen 2. I could have chosen 3. How many options did I have? I had a total of 5 options is what I had. Okay, but in this particular case, we happen to choose 4. Now, for my next event, I'm going to choose another number from what's left. So what's left? Well, now there's these 3 numbers and 4 because the number 4 is gone. So I've got 1, 2, 3, 4 options, those 3 numbers and a 4th option. That's all I have left. So how many options are there here? There are 4. Okay. Now, if we continue using this as our example, let's just suppose that 1 is the number that I picked. So now for my next one, I'm going to choose another number, but now I only have 3 options to choose from. So I could pick a 2, I could pick a 3, I could pick a 5. That's 3 options altogether, 3 different outcomes. And the next time I'm only going to have 2 outcomes. The last time is going to be easy. There's only going to be 1 number left, so that's the number I'll have to pick. So notice what we have here. When I set things up with the fundamental counting principle, because the number of options that I had is exactly equal to the number of events that are occurring, and because I'm not replacing the numbers after I pick them, I end up with 5, 4, 3, 2, 1 as my fundamental counting principle setup. And this is not only equal to the total number of arrangements, we call them ordering, not arrangements, so orderings. Okay. Not only is that the total number of orderings, that also happens to be exactly equal to 5 factorial. And so if I'm working with a problem like this, where I have no replacements, and the number of options originally on the first choice is exactly equal to the number of things that I'm picking, then that's a situation where I will be able to set the problem up with a factorial. So to get my final answer to this, I'm just going to grab my calculator and type in 5 alpha window number 9, 5 factorial, and that's 120. So how many such orderings are possible? 120 orderings. Okay. Now, I'm glad I didn't try to count 120. Okay. 120. We'll trust that the program is right, and we'll take it from there. All right, so this is an example of the factorial and an example of how you might run into using a factorial with a counting problem. All right, so thanks for watching. Have a good one.